Hello students and friends. Two of the problems that I'm going to share to you in this video are actually excerpts of the past video upload on DC circuits concerning electrical power. So stick around, watch and learn. Our example number one is about power output of a battery. So as shown in this circuit diagram, we have a battery with an EMF, electromotive force, 24.0 volts and an internal resistance 1.30 ohms, okay, and a complete circuit with a resistor of resistance 18.0 ohms, right? So there's the battery, and there is an external resistor such as a light bulb. The battery has an internal resistance of 1.30 ohms, while the external resistance big R is equal to 18.0 ohms. The electromotive force of the battery is given as 24.0 volts. The question for letter A, find the current in the circuit. Question letter B, find the rate at which energy is converted from chemical to electrical form in the battery. Question letter C, find the rate of energy dissipation in the battery. Question letter D, find the net power output of the battery. And question letter E, find the rate at which energy is dissipated in the 18.0 ohm resistor. Alright, so we will have the solutions to these questions in just a short while. Our solution for question letter A, finding the current in the circuit. Alright, this current is denoted by capital I, and it is determined by just dividing the EMF, denoted here by the Greek letter epsilon, all right, that is divided by the sum of the internal resistance, small r, and the big R, which represents the external resistance. Substituting, we have 24.0 volts, that's the given EMF, and the value for the internal resistance, 1.30 ohms, and for the big R, 18.0 ohms. Simplifying, we get the value for the current I equal to 1.24 amperes. For question letter B, we are asked to find the rate at which energy is converted from chemical to electrical form in the battery. All right? So that rate of energy that is converted from chemical to electrical form, all right, is exactly what we mean by power. And that power is just equal to the product of the EMF and the current I. Substituting, we have 24.0 volts to be multiplied by the calculated current, 1.24 amperes, and we get the answer, all right, equal to 29.8 watts. All right? In other words, the amount of energy that is converted from chemical to electrical form in the battery is equal to this power, 29.8 watts, which, as we all know, is also the same as 29.8 joules per second. Moving on to our question, letter C. Okay, question letter C is asking for the rate of energy dissipation in the battery. All right, and that is also a measure of the power P, but it's now going to be the product of the square of the current in the circuit multiplied by the internal resistance of the battery, small r. And so, when we substitute the given, calculated I, 1.24 amperes, going to square that, multiplied by the internal resistance, small r, 1.30 ohms, and we will get, okay, we will get the amount of power dissipated in the battery equal to 2.00 watts or 2.00 joules per second. For question letter D, all right, question letter D, we are asked to find the net power output of the battery. So, this is simply the difference between what we got in letter B, all right, the amount of energy that is converted from chemical to electrical energy in the battery, 29.8 watts, minus the amount of energy dissipated in the battery because of the presence of the internal resistance. So that is 29.8 watts minus 2.00 watts, and we get the net power output of the battery equal to 27.8 watts. And finally, for our last question, letter E, okay, we are looking for the rate at which energy is dissipated in the bulb. And the formula for that is just equal to P, the power dissipated in the bulb is equal to the product of the square of the current, I squared, multiplied by the value of the external resistance, big R. All right? Because we said that the same current in the circuit will also pass through the light bulb, and if you're going to multiply the square of that current passing through the light bulb by the amount of the resistance of the bulb, then we are describing, or we are getting the what we call the amount of energy, okay, the amount of energy per unit time that is dissipated. When you say dissipated, this is the amount of electrical energy that is being converted into thermal energy as well as light energy. And that's precisely the function of an electric bulb. So, substituting our given, the calculated current 1.24 amperes to be squared and multiplied by the value of the external resistance big R, 18.0 ohms, we get this power dissipated, okay, in the bulb equal to 27.8 watts. So that's exactly the same value for the net power output of the battery. All right? It's like saying that the net power output of the battery uh, will all be dissipated, okay, in the form of heat or thermal energy as well as light energy, okay, by no less than the light bulb. So you're given two household electric bulbs. Bulb 1 has a wattage rating of 120 watts. Okay, this symbol for wattage, also known as electric power, represents watt. All right, and 1 watt is just actually equal to 1 joule per second. The second bulb has a wattage rating of 60 watts, and both bulbs have the same normal voltage rating of 220 volts. First question is compare the resistance of the two bulbs, okay? And then the second question, which bulb has the thicker filament? justify your answer. Okay, so this is what we will do. Okay, we're going to uh, first identify the variables or the data given in the problem. For bulb 1, we say that it has a power, okay, P1 equals 120 watts. And for bulb 2, that is 60 watts. And since the two bulbs are used or connected to the same power source with a voltage of 220 volts, so we say that V1 is equal to V2, 220 volts. Okay, we need to find the amount of resistance, okay, for each bulb, R1 and R2. All right, so there is a formula that goes like this. To find the resistance R, all you have to do is divide the square of the voltage by the given power. So for R1, that's equal to V squared over power P1. Okay, and substituting, we have 220 volts, square that, and then divide this by 120 watts. The result is we will get a resistance R1 which is 403 ohms. Alright, while the resistance for the bulb 2, whose formula is the same, okay, it's just that we use a different value for the power. So the same voltage, 220 volts, square it, divided by 60 watts, and we will get 807 ohms, almost twice. Okay, R1 is just half the value of R2. Now, if those resistances are related, no, such that R2 is almost twice the amount of R1, okay, what do these values for R's tell us about uh, what we call the thickness of the filament, the bulb filament? Remember, in an electric bulb, it is the filament usually made of tungsten. Tungsten that gets so hot without melting, because the melting temperature or melting point of element tungsten is so high. Okay, so without melting, the filament will simply glow, and that explains why a light bulb can produce can produce light, transformation of electrical energy into light. Now, in answering letter B, we just make use of the relation of resistance, big R, to the following, what you call this, properties, okay, or quantities such as the length of the filament and the thickness of the filament expressed as cross-sectional area of the filament. So imagine the filament to have a cylindrical shape, okay, and therefore it has a certain thickness, okay. The area, of course, is just the, how do you get the area of a circle, for example, all right? The cross-sectional area simply means we are getting the area of that circle, no? That describes the cylindrical shape of the filament. So it is pi r squared, correct? The greater the radius, okay, of that filament, the thicker it is, and therefore the greater the cross-sectional area. All right, but it is the thickness or the area that we are trying to compare. Okay, uh, compare the area or thickness to the resistance of the bulb. All right, and since earlier we got in letter A that the resistance R2 is higher compared to R1, assuming the length of the two filaments, okay, the lengths are the same. and they are made of the same kind of material. For example, both are made of tungsten, okay, whose what we call resistivity constant. This Greek letter rho stands for resistivity. It's like the opposite of conductivity. All right. So the resistivity value, conceptually, it tells you the ability of a given material to oppose. All right, to oppose the flow of charge. So that is what we call resistivity. So assuming that is constant and the length of the filaments are constant, so we are only relating the thickness in terms of the cross-sectional area to the resistance, okay, we say that the bulb with the smaller resistance has the thicker filament, and that is bulb 1. We are down to our last question. Factors affecting power. The problem is Robert and Princess are discussing whether an electric heater with a large or with a small resistance will yield the greater heat output. Robert favors a small value of R because he says power is equal to V squared over R. Princess favors a large value of R because, according to her, P is equal to I squared times R. Now, what is your own conclusion? Okay, so let us first clarify some terms here. When you say greater heat output, we actually mean the uh, the amount of uh, energy, okay, that is transformed in using electric heater. Of course, we are uh, producing heat or thermal energy, okay, is being produced by heater, okay, with the use of electric energy. Okay, or electrical energy is being converted to thermal energy. All right, and uh, according to uh, Robert, a small value of R, meaning the resistance of a heater, okay, the small value of resistance of the heater is what can produce the greater heat output, because he is using this formula for power. All right. Okay, so according to this formula, at a glance, tells you that P is inversely proportional to R. So that's the reason why Robert thinks that the smaller the value of R, the greater the amount of heat produced per unit time. All right, power. While Princess, okay, favors a large value for R because of her belief that the power is equal to I squared times R, and that using this example or equation, okay, it looks like R is directly proportional to the power. So that the bigger the value of R, the bigger the power. So which between these two students, okay, is correct? All right. So again, we will identify the given data. Okay. For heater number 1, which is uh, the heater used by Robert. Okay. The given R, for example, is 1 ohm. Okay. There is a need for us to assume certain values for the resistance. And for simplicity, we choose a value that is a small value, such as 1 ohm. And that for heater number 2, the resistance R2 is equal to 2 ohms. Okay. Now, uh, as we all probably know, okay, these heaters will be used, okay, using our household voltage supply. Our household voltage supply, for example, okay, in the Philippines, we are using 220 volts. All right. But in other places, probably they are using 120 volts or probably 110. Okay, it depends on the country. All right. But for simplicity, once again, we just choose a small value for the voltage, V1 and V2 being equal. Let's say it is equal to 20 volts. And we are going to calculate for the power, okay, P1 as well as P2 using both equations mentioned by Robert and Princess. So here we go. Okay, as claimed by Robert, P1 is equal to V squared over R1. Okay, and substituting the given voltage and R1, we get this power P1 of 400 watts. While, okay, for the higher resistance heater, okay, we get, using the same formula, we get 200 watts. And obviously, okay, obviously, it looks like that Robert's claim is correct, okay, because the heater with the small value of R, all right, has the greater power output, okay. That is the result of Robert's computation here. Let's look at Princess solution. Okay, for Princess, she uses the formula P1 or power is equal to I squared times the resistance. And using the two given values for the resistance, R1 and R2, okay, the first heater also produces the same power of 400 watts, the same as what Robert's formula, okay, yielded. That's also true for the second heater, okay, the same power output was produced, 200 watts. But, again, who between them, between Robert and Princess, is actually correct. Okay? P1 refers to the heater, okay, with the lower resistance, while P2 refers to the heater, okay, with the higher resistance. So, according to Robert, the small value of R, okay, will yield the greater heat output, while Princess claimed that the larger value of R, okay, will yield the greater heat output. So, who between the two uh, students is correct? Of course, it is Robert. You know what the scientific basis can be cited why Robert's claim is correct? All right. It is the fact that both heaters, okay, will be connected to the same power supply whose voltage is the same, okay, such as what we use here, 20 volts. So, in his equation, Robert's equation, that power is equal to V squared over R, okay, he is correct in saying that a small value of R, okay, will produce the greater power because uh, the voltage here is held constant. All right. V2 is constant, and therefore it is correct to say that the smaller the value of R, the greater is the power output. Okay. Whereas in Princess equation, okay, the current I is not constant. Okay. The current I is not constant. In fact, if you notice in her substitution of the given, okay, it can be computed that the current for a given voltage of 20 volts and for a given resistance of 1 ohm, okay, the current in fact is 20 amperes. All right. But for the higher resistance of 2 ohms, okay, with a given voltage of 20 volts, okay, the corresponding current in fact is lower. So, it is not correct to say, using Prince's formula, that the greater the value of R, okay, the greater the value of output power is. That is not quite correct, because that's only true if the current, or I squared, is constant. And that explains why Robert is the one that is correct. Thank you very much. Okay, that ends our uh, tutorial, and hope to see you in my future video tutorials. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.